Hello. So, in this one, we are going to discuss more about the functions and continuity, and we are going to also discuss about differentiation in general for analysis. So, this kind of differentiation would be mostly used when we will be doing probabilistic inequalities and probabilistic solutions, more like Markov chains and stochastic processes. So, this analysis portion which we are currently studying, the like we have already studied about some linear transformations, we have studied about functions and continuity and stuff like that. Now, functions and continuity were a chapter where we understood how do we actually define continuity for functions of higher dimensions, though that is like functions which go from one Euclidean space to another Euclidean space and stuff. But it is not entirely clear as to how we can understand if f from r to the power n to r to the power m is differentiable, which means that we know that f from r to the power n to r to the power m is differentiable, but we want to understand what is the condition of so, right? So when it was continuous, we understood that for every epsilon greater than 0 there would exist a delta greater than 0 such that 0 less than norm of x minus a less than delta, and we would say that norm of f of x minus b should be less than epsilon, right? This would imply that limit x tends to a, f of x is equals to b, right? Now, this is how we used to define the things. Well, obviously here x belongs to r to the power n, a belongs to r to the power n, while b belongs to r to the power m. Okay. Now, this was how we defined continuity, but for differentiation things would take a little bit of a wide turn. So let us start it. So we want to recall first about our one-dimensional differentiation process. So derivatives in one dimension. So how do we do derivatives in one dimension? We knew that a function f from r to r is differentiable at a belongs to r if there is a number f dash a such that we had limit h tends to 0 f of a plus h minus f of a by h equals to f dash a. So what we used to do is that let me just write down the definition for one dimensional case. Such that limit h tends to 0 f of a plus h minus f of a whole divided by h is equals to f dash a. So this limit, which is denoted by f dash a, is basically called the derivative of f at the point a, and that is how we used to find out derivatives, right? Now, what happens when we switch this definition from this lower dimension to the higher dimensions, where we are no longer concerned with r to r, rather than we are looking at functions from r to the power n to r to the power m. So the heading should be derivatives in higher dimension. Well, now if f is from r to the power n to r to the power m, and let's say there is a point and f is differentiable at a small a belongs to r to the power n if there exists a linear transformation lambda from r to the power n to r to the power m such that limit h tends to 0 norm of f of a plus h minus f of a minus lambda of h divided by norm of h equals to 0. And this norm of h is basically this lambda of h is basically that derivative. It's called the derivative. In the one dimensional case, this lambda of h can be defined as follows. Lambda of h is f dash a into h. So this is basically the derivative definition for higher dimensions, and we can often say that lambda plus f of a is a good approximation to f of a plus h, or let's say f to f at a, but this is basically the definition that we are going to follow. Now this linear transformation lambda is called, so lambda of h is called as df of a h, which is the derivative of f at a. Which is the derivative of f at a. So like this is how we are supposed to find out that this things actually work together. Now a property that I'm going to follow from here on is as follows. Let me just write down the claim or the lemma. So if f from r to the power n to r to the power m is differentiable at some a belongs to r to the power n, and we have this following limit, that is limit h tends to 0, the norm of f of a plus h minus f of a minus lambda of h divided by the norm of h which is equal to 0, then the linear transformation lambda is unique. So what we want to basically understand here is that for a given function, if it is differentiable and it is differentiable at some point a, then the derivative of it is basically unique. So as you understand from the last section that the linear transformation itself is the derivative of the function, right? So that linear transformation, whatever it is, that must be the derivative of it, and it is unique, so there cannot exist two different derivatives of the same function at the same point. Okay, so how do we prove it? Well, since we already have proved things like this in the past, which is if you want to prove something is unique, so in mathematical terms what you do is you on the contrary assume that that is not unique, and you assume two of them. So you assume two of the different things which have the same property, and then by some way you would like to show that those two things are equal. That is, you want to take two arbitrary linear transformations, let's say lambda and mu, and you would like to say that both of these are derivatives of the function f at the point a, and then somehow you would like to show that basically lambda is equals to mu, which would mean that no matter how many different arbitrary derivatives you might have or you might consider, all of them would be equal, and basically there is only one derivative that exists and is unique. So let us proceed to the proof. Let us assume on the contrary that so we assumed on the contrary that lambda and mu are the two linear transformations that satisfy so they both will satisfy the limiting condition, and the domain and range of them would be r to the power n to r to the power m as well. So let me write it down. So this will be the two conditions that lambda and mu shall satisfy, and well, you can see a lot of similarities in these two, and something that we can do using these two functions. So how do we proceed from here is something we have seen before when we were doing linear algebra. So what we want to do here is we would like to show that lambda is equals to mu, or rather lambda of h equals to mu of h if we are considering the argument as well. But in general the two linear transformations should be equal. And now how to show that two linear transformations are equal? One way is to consider arbitrary argument x and show that lambda of x equals to mu of x. And to do that, we would first need to understand how to use this to limits, because those are literally the only thing given apart from the fact that lambda and mu are linear transformations, or basically linear functions. So let us proceed on that. We start with the fact that limit h tends to 0, norm of lambda of h minus mu of h divided by norm of h. Now we would like to evaluate this limit. Now understand that f of a plus h minus f of a is basically a finite it's a finite vector, because well, it belongs to r to the power m. So let me just erase this part, and what we need to do here is now if we set d of h equals to f of a plus h minus f of a, which also belongs to r to the power m, we can write the limit which we want to calculate as follows. So this can be well written. Now we understand the properties of norm, where we can understand that norm of a plus b is basically less than or equals to norm of a plus norm of b, right? So we can write and this is 0 because we know from the given facts that d of h is f of a plus h minus f of a. Now if we name the two conditions 1 and 2, so in one of the conditions it is less than equals to 0, and in another one of the conditions it's greater than equal to 0. It's more like a sandwich theorem. Therefore so this gave us lambda h minus mu h norm divided by h's norm when h tends to 0 is equal to 0. Now this is true for h, right? So this limit goes to 0. Now we can understand that since h is not equals to 0, we must have lambda of h minus mu of h going to 0. Now if h were to be tx, where x not equals to 0 and t tends to 0, we can write, so if h equals to tx where x is not equals to 0 and is arbitrary where t tends to 0, then so t is just a real number here, and this is not a limit where, so here t is just like a real number which is a constant, and x belongs to r to the power n, right? So what happens here is, since lambda and mu are linear operators, we see that since t is a constant, we can write this as t into lambda of x minus t into mu of x divided by t into mod of t into norm of x equals to 0. And this would become mod of t into norm of lambda of x minus mu of x divided by mod of t into norm of x equals to 0. And the mod t is cut off because it's inside the limit and t is not equals to 0 inside the limit. Therefore there is no condition for limit t tends to 0 anymore, and we see that lambda of x minus mu of x, the norm of them, is equals to divided by the norm of x is equals to 0, right? This is for all x belongs to r to the power n. Since x not equals to 0, norm of x would not be equal to 0. Therefore, norm of lambda x minus mu x is equal to 0. And we have known from the properties of norm that if the norm of a function is 0, that function is identically 0, right? So lambda of x minus mu of x is identically equal to 0, which means lambda of x is equals to mu of x, right? So this all correlates the fact that the linear transformation is unique. Now what you will get in supplement to this kind of solutions is that you would also have the introduction to derivatives chapter using limits and using chain rule, both of them in embedded inside this video, so that you can understand clearly what's going on. So you'll find that after this video how to do the derivative part and how to do the derivative sections. But this would signify that lambda of x equals to mu of x. That means the linear transformation is unique. Okay. Now what we would like to do here is we would like to answer a few questions after this, and we'll try to make sure that the problems here are not as difficult as they look, because we'll try to break them down into step-by-step solutions, and the exercises and the solutions we are going to do would follow in the next video. The derivative of a function f of x at x equals to a is given by f dashed of a equals to limit x tends to a f of x minus f of a whole divided by x minus a. So this is the definition of derivative of a function, and we can use it to our advantage to find the different derivatives. Now let us begin by solving different basic derivatives first, and then we can do the other ones later. So what are the derivatives that we are going to find? So trigonometrical identities are a great way to start off this list of chapters. So trigonometrical identities. Trigonometrical identities are a better way. So the derivatives which we are going to find is sin x and cos x. So let us begin by one of them. So sin x, let f of x equals to sin x, then the derivative of f of x is, so now we try to find the derivative using first principles, and it won't be that much hard, because as we have already encountered this kind of problems before, we shall be accustomed by now to as to how to approach this kind of problems and how to solve the particular limit. So here, as you can see, the question asks us for f of x equals to sin of x. So the limiting definition would be limit x tends to a f of x minus f of a by x minus a, right? Another definition for the limit is what I am going to write now, is the definition what we are going to use while solving the problems. This is limit h tends to 0 f of a plus h minus f of a divided by h. This is a more standard definition of derivatives, and I think this is more useful than the other one, because the first one is usually the one where we convert from limit to derivatives, but this one actually helps us to find the derivatives in terms of the functions, elementary functions, directly from the limit. So using the value of f of x, we can write this as like this, right? Now we can use the formula using the formula for compound angles, that is, we can add and subtract angles inside sine, and we can also express them. So we can use the formula sine of a plus b equals to sine b cos a. So this is the formula, right? So using this formula, we can see that sine of a plus h similarly would be now. When this is done, what we can do now is we can find the limit L. Actually here we do not read the answer L, we already have a name for it. So f dash a is equals to limit h tends to 0 sine a cos h plus sine h cos a minus sine a divided by h, right? So what we can do is limit h tends to 0 sine h by h into cos a. So we can just take the second term here, and we can take the first term common, and we can write limit h tends to 0 1 minus cos of h by h, right? So this limit is 1, so it becomes cos of a, because we have learned about the limit x tends to 0 sin x by x in the previous videos. And the next one sin a into, now we first use the formula for 1 minus cos theta is equals to 2 sin square 2 by theta. So using that formula, it becomes minus 2 sin square h by 2 by h, and this limit goes to 0, because firstly sin h by, if it was sin h by 2, we could have found the answer, but since it is sin square h by 2, it goes to 0. So the answer is cos of a. So the derivative of sine of x at the point a is cos of a, right? Okay, we can do a similar calculation for cos of x as follows. So case 2 is, now the derivative would be defined as follows. Defined as follows: f dash a would be equals to limit x tends to a f of x minus f of a by x minus a from which we can substitute h equals to x minus a to find the new definition which was more useful to us, which is like f of a plus h minus f of a divided by h, right? Now this would give us limit h tends to 0 cosine of a plus h minus cosine of a whole divided by h, right? So this means now we have to use the formula now. Trigonometry that cos of a plus h is equals to cos a cos h minus sin a sin h. Using this formula, what we can do is as follows. Using this, we have f dash a equals to limit h tends to 0 cos of a cos of h minus sin of a sin of h minus cos of a divided by h. So we can again distribute it as follows. Take cos of a common and we can write it as limit h tends to 0 cosine of h minus 1 by h minus sin of a common limit h tends to 0 sin of h by h. As we know from the previous example, this limit is 0, so this is 0 minus sin of a into 1 because this limit is 1 as we have done in previous examples. So the answer becomes minus sin of a. Okay, so that's the derivative we were trying to follow. A third example now could include the derivative of e to the power x. Derivative of e to the power x. So let f of x equals to e to the power x. Then let us evaluate the derivative at the point x itself. So what we are going to do is we are going to write it like this: h tends to 0 f of x plus h minus f of x divided by h. Okay, so this tells us limit h tends to 0 e to the power x plus h, because f of x is e to the power x. So f of x plus h would be e to the power x plus h minus e to the power x whole divided by h. We using the rule for indices, the law of indices, we can write this as e to the power x into e to the power h minus e to the power x whole divided by h. Now we can take e to the power x common as the limiting variable is h, so e to the power x is basically a constant here. We can write e to the power x into limit h tends to 0 e to the power h minus 1 divided by h. And as we know from previous experience, this limit is again equal to 1 as I have proved. So the answer is e to the power x. And as you can see, the derivative of e to the power x is e to the power x itself, which actually means that we can find the derivatives very clearly here, and this is the only function whose derivative is itself. Now once we are clear with the basic definitions of how to find derivatives, I can give you a list of basic functions and their derivatives. So let me write it down. List of common functions and their derivatives. So now I'm going to write down all the functions and their derivatives, and from the next video onwards we would be trying to implicate them and learn about more about the chain rule. Okay, so the more we learn about the chain rule, the better. Okay, so derivative is usually written as d dx, where x is the derivative variable, and in bracket we write the function which we are differentiating. So this is the format that I am also going to use. So these are the three functions. Firstly, d dx of x to the power n is n into x to the power n minus 1. d dx of ln of x is 1 by x. d dx of a to the power x is a to the power x into log of a. Number 4. Is a to the power x. Number 5. Number 6. Of tan x is basically equals to sec square x. Number 8. d dx of cot x would be equal to minus cosec square x. So I think these are some of the basic things, and there are other things as well that you need to know, but for the time being this should do. This should actually work pretty well. So let me write down some more rules. If fx and gx are two differentiable functions, then d dx of fx plus gx is equals to d dx of fx plus d dx of gx. So basically, if you are given to find out the derivative of the sum of two functions where both of the functions are differentiable, then the answer is basically the derivative of the first function added with the derivative of the second function. Similarly, if you are given something like this, where you have given the multiplication of two functions, then what you can do is try this. And finally, if you are given two functions in the form of division like this, then the answer is simply gx whole squared gx into f dashed x minus fx into g dashed x. And obviously here g of x not equals to 0. So these are the three rules also that you need to follow when solving for derivatives. And along with this, the most important theorem of all is the chain rule, which we shall do in the next lecture, where after that we can be free to evaluate any derivative we want by hand. It's a magical rule, so evaluating derivatives won't be a problem anymore once you learn and once you get a hang of that rule. But before that, you need to be very much confident about all these formulas. You need to memorize them by heart so that you can just tell them at your lips. Let us begin with the chain rule. chain rule states that the derivative of a composite function where f of x is continuous for all x belongs to u, where g is a function such that it goes from d to u, and g is continuous and differentiable at x belongs to d, then the derivative of the function f of g of x is given by f dash of gx multiplied by the derivative of gx. So it might look that it's not such a big result, and okay, the definition might be a bit more complex, but the result itself says that the ddx of f of gx, considering all the other technicalities solved, that f is continuous at g of x and f is differentiable at g of x and g is differentiable, we can say that the function f of gx can be differentiated by just differentiating the function f at the point g of x and then just differentiating g of x at the point x and multiplying them together, right? But this simple definition is the key to solving all of derivatives problems, as you can see now. So if you remember the basic derivatives, which I can recall one by one, it's like x to the power n is n into x to the power n minus 1, sin x is cos x is minus sin x and stuff. Then logarithm of x is 1 by x, e to the power x is e to the power x itself. Now we can try and find out the derivative of, so we are going to do a bunch of problems now. So let us do ddx of e to the power ax. So ddx of e to the power ax. So first recall the basic function. The function, what it starts with? It starts with the function e, right? E to the power something. Now, what is the most basic representation? It's e to the power x. So if you remember, ddx of e to the power x was e to the power x, right? So we are going to copy this and write the answer itself. That is, the answer should be whatever is given. So e to the power ax, right? So pretend as if this function was e to the power x only and write the whole function down. But then multiply it with, go to the next level of the function where the anomaly is present. So it should have been e to the power x, but it isn't, right? What is there instead of x? It's a of x. So now it should be ddx of ax, where a is just a constant, and when you do a constant x, a times x, the ddx of x is just 1 and constant just comes out. So the answer becomes a into e to the power ax. This is because ddx of x is just 1, and also ddx of a constant c times any function f of x is just c times the derivative of the function. So the constant just remains multiplied throughout. Okay, next example. Because the more examples we do, the more it would be easier for you to understand. ddx of ln of, let's say, x squared. So how do we do this? Well, first we try to think what the ddx of ln of x is, because the first function is ln of x, right? So ddx of ln of x is equals to 1 by x, right? So pretend as if this function is ln of x, and we write the derivative as 1 by x square. So do not directly write 1 by x, because you just need to pretend. But when you are going to write the derivative, you are going to write the same thing, and instead of x, whatever is present, you are going to use that. But you are just pretending it is x, right? Now you multiply and you do the derivative of the next level, the expression which is present instead of x. So x square is present here, so we do x square. So it is 1 by x square into ddx of x square by the rule for differentiation of powers is 2 into x to the power 2 minus 1, right? So it will become 1 by x square into 2x, which will give you 2 by x, right? Okay, one more. Let us try to evaluate ddx of log of sin x. Now how many layers are there? Let me just clarify this like this. Layer 1 is the first layer of function. This is log. So layer 1 is log x. And what is layer 2? Layer 2 is sin x, correct? So it is log x and it is sin x. Now the answer can be written directly if we have that in mind, because we differentiate one by one and we keep on doing that until we reach the inner bottom where x is present. So ddx of log of sin x is simply equal to, firstly we do the ddx of log x, which is 1 by sin x, and then we do the differentiation of sin x, which is cos x, right? And cos x by sin x is simply cot x. So you see we have got the answer. ddx of log sin x is just cot x. Okay, so this is not really a very hard one to be done. Let us move to other examples. We need to find the derivative of this function. So here comes the harder ones, or rather you can say the more complex ones, because if you know what to do, I do not think this would be at all hard for you any more than it for the last problem was. But then again, this would be a bit more calculative, right? So we first need to understand the layers and stuff. So what is layer number 1? Layer number 1 is of course sine of x, right? Sine and some x inside it, which we are going to pretend is x. Layer 2 is of the form fx by gx, right? Layer 2 is of the form fx by gx, which we learned before, that the derivative of two functions can be evaluated how? I'll just write it down here, that ddx of fx by g of x can be evaluated as fx into g prime x, right? What is layer number 3? So in fx there are two layers, right? In fx there are two layers. How many layers are there? Fx has a layer which says that the inside function is x square plus 2. Similarly, gx has a layer which says that the inside function is e to the power 5x plus e to the power x, right? But these layers do not really matter because we already have a fx by gx thing here, right? So we are going to use them here directly. So let's do this. Let us first define the function as capital F of x equals to sine of, let me just copy it, log of x square plus 2 divided by e to the power 5x plus e to the power x, e to the power 5x plus e to the power x. Then f dash x would be, so firstly the derivative of sin x is cos x, so we first have this right, multiplied by, now we have the part where we do actually fx by gx thing. So this is gx, this is fx, so this should be squared. Squared means multiplying by 2 in the power, which is e to the power 10x plus 2 e to the power x. Then we have e to the power 5x plus e to the power x into the differentiation of log of x square plus 2. So first we pretend it's a log of x, so we do a by x square plus 2, and then we do the inside, which is x square plus 2, differentiating which you get 2x, because the differentiation of a constant is 0, and if you remember, addition of two functions when differentiated is basically equal to derivative of the first function plus derivative of the second function. So here derivative of the constant is 0 and derivative of constant of x square is 2x, so 2x minus ln of x square plus 2 plus remains like that. And now we do the exponential. So firstly the exponential remains the same, so it's e to the power 5x plus e to the power x multiplied by, we do the 5x plus e to the power x, which is 5 plus e to the power x, so 5 plus e to the power x. So we can write it clearly here, cos of ln of x square plus 2 by e to the power 5x plus e to the power x multiplied by, now we can do a simplification here, x square plus 2 into e to the power 10x plus 2 e to the power x, and we can write it as follows: e to the power 5x plus e to the power x taken common, we have 2x minus x square plus 2 into ln of x square plus 2 into 5 plus e to the power x, and we can cut off this 5x plus e to the power x and this to give you the final answer, which is cos of ln of x square plus 2 divided by e to the power 5x plus e to the power x into 2x minus x square plus 2 into 5 plus e to the power x into ln of x square plus 2 whole divided by e to the power 5x plus e to the power x into x square plus 2. So this is our final answer, and obviously some multiplication in between. So this is the final answer for the problem. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.